Benedetto from Terra Foundation and CIST. Elena, you can share your screen already, I think.
And
okay, we see full screen and we hear you.
Okay, yeah. And you also see the mouse moving?
Yes, we see.
Perfect.
Perfect. Go ahead. Thank you.
Good morning, everybody. Today I will discuss a very special beam manipulation, so injection into synchrotrons. It is a quite specific topic, and for this I will build on what you heard yesterday from Mariusz. So I will have a small recap of accelerator physics, and then I will introduce you 3 methods for which you can have injection for ion synchrotrons and protons, of course. So single turn, multi-turn, and charge exchange. Okay, for the recap, I try to use this very same figures and formalism of Mariusz so that you can navigate our lectures. And for the injection part, I took most of the material from this school. And I invite you to check the website because you find a lot of information, and which is very useful on injection and also extraction and beam transfer. So let's start. But first of all, what is injection? Well, whenever you have an accelerator, a circular machine or so, you need to inject beams in it. So be it a medical facility, and this is the planned CIS facility that we are going to build also with the help of HITRIplus. Be it the LHC, which is the big one, and the rings of the complex. So injection in our machine is here. Injection at CERN is done here. Okay, so quite a lot of places where you can have injection, different kinds of injection. Now, I will build on concepts that were introduced yesterday. So stay with me and let's see what is the important concept that I will use in my lecture. Okay, first of all, the reference orbit. The particles and indeed the entire beam will not be on a circle, but they will oscillate around it. Okay? The number of oscillation is called tune, and it must not be an integer. Okay? So after one turn in the synchrotron, the particle or the beam will not be at the same position as before. Okay? So you see it here. This is to avoid resonance that will cause you beam losses or other disruption that you don't want. Or maybe, as you will see in the next lecture by Rebecca, that you want. Extraction, slow extraction is a way to induce controlled losses and extract your beam on a resonance. Then, to describe the beam or the particles, you work in a 6-dimension phase space. So you describe the beam with the 3 coordinates, x and y in the transverse plane, and z. And these coordinates are the deviation with respect to the reference trajectory. Reference trajectory is your circle in the machine. You compute deviation from that. And then you have other 3 coordinates. In the longitudinal is momentum offset, and then you have the divergence. Divergence is similar to the momentum of the particle, momentum, which is the velocity. But we prefer to express it in divergence, which is a kind of an angle between the direction of the beam. So yeah, it's kind of the direction of the beam. So the angle between its momentum and the longitudinal coordinate S. Now, if the beam is not coupled in the 3 planes, instead of talking of the 6D phase space, you can analyze subspaces, 2D. 2D is more handling. And then if you stay in 2D, and there is no coupling, you can, by putting together all your elements in the ring, you saw it yesterday from Mariusz, you can write the so-called Hill equation. As you see, this is the equation of a pseudo-harmonic oscillator. You recognize the second order derivative, a coefficient which is somehow the frequency of oscillations and the position. However, this frequency depends on the position S. Of course, you can do the same in the vertical plane. Here now we will stay on the horizontal. Okay, now since it's similar to the harmonic oscillation, the solution will also be similar. But because of the frequency of oscillation depends on the longitudinal coordinate, also the amplitude and the phase will depend on S. Okay, we call it pseudo-harmonic. Now, if you write the solution, so for the position and for the divergence, you see that this is this represents an ellipse, and this is the ellipse that you saw yesterday from Mariusz. This is an ellipse has a lot of meanings. Here in these slides, I want to highlight the fact that at every turn in the ring, the beam will be on a different position on this ellipse. Okay, first turn, second turn, third turn, fourth turn, etc., etc. Unless the tune is an integer. If it was an integer, after one turn, it would return at the initial position. But this is something that we don't want. We want it to rotate along the ellipse. Okay, we call it the accelerator ellipse. Okay, I stay in a position in a ring and I look at the particles, turn after turns. And this is what I see. Now, we also have another ellipse. This is the beam ellipse. This is the ensemble of particles which are also organized in an emittance. And what is important is that these two ellipses, the beam ellipse and the accelerator ellipse, in a synchrotron should have the same shape and orientation. So this ellipse, whether it is the accelerator or the beam ellipse, will change shape along the longitudinal coordinates, so along the ring circumference. But okay, after one turn, you will get to the same shape. And important, the area of this ellipse is a constant, is an invariant of motion. And this is very important. Okay, so now ellipses are pretty difficult to deal with. That's why we want to have a coordinate transformation, and you see it written here, so that you go from the ellipse to a circle. And this is much better to handle, especially because while this ellipse was moving along the circumference, this circle is the same wherever is your position, because you have divided, like the x is divided by the beta function, which depends on s. So now this quantity is the same wherever you are, and the same for the divergence. So from now on, I will discuss about this phase space, where this axis is the position. So this is something physical that you can see. And this is somehow related to the velocity of the particle, to the direction in which they move. So if they can go straight, or they can form a divergent beam or a convergent beam. Okay, now, what is the injection? The injection means filling the synchrotron with charged particles. So far, so good. But what it is important is that you should have the correct phase space distribution, and we talk about matched beam. So we must inject a beam whose ellipse has the same shape and orientation of the accelerator ellipse. We have to inject this particle on the correct orbit, and in the longitudinal plane also at the correct phase with respect to the RF cavities. The goal of this exercise is to minimize beam losses and the emittance blow up. Emittance is a measure of the beam size. We have for the time being, let's start with a simpler injection, a single turn. What do you need for injection? For the injection, you have your circumference. We call it a ring closed orbit. Eventually, it will close and make the circumference. And then you have the beam coming from a transfer line. Here you have your source, your linac, and then a transfer line that will bring the beam to the synchrotron. And then you have a septum. A septum is a thin foil here, which separates a region with field from a region without field. In the region without field is where the synchrotron is. So the beam, if it was there, it would feel zero field, zero deviation. But here in this space, you have some field, whether electric or magnetic, that induce that bend this particle. And from this angle, you get a different angle so that you can get closer to the closed orbit in the ring. And then at the end, you will have a kicker magnet. This is another bending magnet, but it's very fast. Huh? It's really fast. And when the beam is entering, it compensates for this angle that has, give a very fast kick that brings the beam to the correct angle and on the closed orbit. And from there, the beam will start circulating. The kicker has to be so fast that when the beam comes back after one turn, and it takes microseconds, so 1 per mil of a millisecond, this kicker is already off and the beam is unperturbed. Now, this is to show you how a septum look like. The septum is here. This is the thin foil. And on this side, you have the vacuum chamber of your synchrotron where there is no field. On the side of the incoming beam, this is an electrostatic septum, so you have an electrode. And here you have some electric field which bend the beam. So on this side, you have the circulating beam, which goes straight. On this side, you have the injected beam, which is bent to follow the circulating beam. You have a similar picture for the magnetic septum, same concept this way. So the circulating beam is on this side, and here is the area with the field, and this field now is generated by a magnetic field. It's always bending the particle. And you see it here, this is the vacuum chamber of the synchrotron, and this is the injected beam which gets deviated in order to then join the circulating beam, and this is the septum. This is a magnetic septum. Okay, now, I told you injection is injecting particle with the correct phase space and with the correct trajectory. What happens if this is not the case? In this case, the beam is not injected at the center of the acceptance of the phase space. This is always the XX prime phase space. The beam, you see, is not injected in the center. So what happens? First of all, it will start oscillating, but then, because of nonlinearity, it will start filamenting. So after a few turns, you will have such a situation, and then this, and even worse and worse. So you see, you have started with such a nice and very dense, bright, we call it bright beam, slightly offset, and you end up with a much less dense beam. So this emittance has a very large beam size. It has been blown up. So you see that here you have lost your brightness. The beam was nice and compact, and now is not any longer. Perhaps you wanted them. There are some occasions where you want to dilute the beam, but most of the time, this is something that we want to avoid. The same happens if your beam is not matched to the ellipse. So again, the same. So this is your ellipse, the accelerator ellipse, and your beam, instead of having the red shape, it has this shape here. Again, you see this beam is not matched. So it will start oscillating and pulsing, But then, due to nonlinearity, it will start again filamenting, so here and there and there. And finally, again, you will end up with a more large beam than before. Again, this is something that you may want, but most of the time you want to avoid. Now, let's go to the second kind of injection, multi-turn injection. So what happens if the intensity coming from the source is not enough? You have to inject multiple turns. And for this, you use a slightly more complicated system. You see here you have always the ring orbit. Here you see the beam coming from the transfer line, entering the septum and getting deviated as before. But now we have at least 2 kickers. Sometimes we have 3 or even 4. That creates the so-called orbit bump. Okay, so it gives a kick that bends the beam up, makes this bump, and finally is brought back to the reference orbit by another kicker. Like this, you can get closer to the septum with the orbit, and you can inject in this way. Now, turn after turn, this bump will decrease, allowing you to inject multi-turns. Now, this is a nice animation done always by Chiara Brack and available at that school. What happens in the phase space? This is again the phase space. This is the 0 position of the beam pipe, so the center of the beam pipe, and this is the septum. The septum is at a given position X. And then the beam coming from the transfer line is here at position 1. And because of a bump, you bring the closed orbit here at this point. And then you start injecting. And what happens when you inject? When you inject, the closed orbit will go in this direction. You will see it. So you inject the second turn, the third, the fourth, etc., etc. You see that the closed orbit is getting closer to the center. And you start injecting particle after particles. Now, I will do it once more. What is the tune? The tune, we said, is the number of oscillations in a ring, and is not an integer. In this case, the tune has a fractional part of 0.25, so 1/4, meaning that every turn, the beam, injected beam, so number 1, will make 1/4 of the total circle. Oops, you see it, 1, 2, 3, and 4. You see? 1/4. Etc., etc. So this gives you an interesting way to fill the accelerator ellipse with more than one particle. Another thing that you can notice is that at the beginning, the incoming beam is nice and round, but then after a few turns in the machine, the beams gets a different shape. Yes, because every time that it intercepts the septum, some of the particles are lost, unavoidable. However, losses are at low energy, so we can deal with them. So, to summarize on this multi-turn injection part, this is used when we need to inject a higher intensity than what provided by the source. And this is the case especially for medical machine, and in particular for our seized synchrotron, because we design it for intensity which are 10 times higher than the European medical machine. Tomorrow I will explain you why. These are simulations done by a student who joined us a few years ago, so from University of Sarajevo. She prepared the tools to study multi-turn injection, and this is one of the first results. So very similar to the plots that I showed you before, but this is simulations done tracking particles turn by turn. And maybe one of you will be the next student and will really study the details of this injection in our machine. Who knows? What you can see is that the final emittance will be much larger than the emittance of the incoming beam. This is the incoming beam. This is the final emittance. And that you will have losses because the beam will not keep their shape, but they will be scraped off at the septum. However, these losses happens at low energy, so they are not really dangerous. Now, beam is getting much larger. Maybe it's something that you don't want. So what can you do better? Well, you do charge exchange multi-turn injection. This is quite complicated, and I only want to show you for you to get some idea. First of all, we had only ions with the same charge. Here, this is done in the CERN PS booster. Here you have protons circulating. They are bent by a set of bending magnets. They form a chicane, so they see they are bent up and then down and then back to the closed orbit, same as before. Oops.
Elena, your time is up.
Okay, done.
Yeah,
and then you have an incoming beam, which is not protons, but it's H minus. H minus has a different charge, therefore it's bent in the opposite way. But then at some point there is a stripping foil who strips out the 2 electrons of this beam and transform it into protons that therefore can go back with the same beam as before. Like this, you can inject always in the same space and obtain very, very bright beams. But there are some other things that does not allow us to use it in our machines. So in conclusion, injection must be done carefully to preserve the beam emittance. It's very convenient to work in the phase space. And then I show you these 3 different kind of injection. And we, in medical machine, we normally use multi-turn injection. Thank you very much.
Thank you very much, Elena, for this very instructive presentation and making the connections between the different presentations. I would suggest to go directly to the next presentation and take questions for the whole session at the end. So the next speaker is Rebecca Taylor from Imperial College that is working now at CERN together with Elena on her PhD. Rebecca, please.
Hello, yes, thank you very much. So